webinar organized by the CLIVER Research Focus Group on Marine Heat Waves. I'm Antonietta Capotondi, and I co-chair this group together with Regina Rodriguez, who is also here online. And so the main goal of this research focus group is really to advance research on the topic of marine heat waves, but also trying to connect activities and research that is done across different communities and different groups. So the webinars are a way to try to reach out and kind of bring the community together. So our first webinar was explored extreme warming in Northwest Pacific and the ocean-atmosphere interactions there. And today we will continue on a similar theme, but exploring different aspects of air-sea interactions in the context of marine heat waves and the effect on land condition, on adjacent land conditions. So thank you everybody for joining, and I'm going to leave the floor to Regina, who is going to introduce the speakers.
Okay, so our first talk is be given by Ségolène Berthou, and she did her PhD on heavy precipitation in the Mediterranean and its sensibility to sea surface temperature at the Laboratoire de Météorologie Dynamique in Paris. She joined the UK Met Office 9 years ago in climate science, where she works on high-resolution global and regional climate models with Malcolm Roberts and Lisa Kendon. She's now managing the regional couple system team, and she's presenting work done by her team and many collaborators across British and Irish institutions on the unprecedented June 2023 marine heat waves. And during today's webinar, she's going to talk about marine heat waves in the Northwestern European shelf, forcing and feedbacks on the atmosphere. And I'm going to give the floor to her, and then later on I will introduce our second speaker. Please, Ségolène, you can start.
Thank you. Perfect, thank you.
Thank you.
Can you all hear me well?
Yes.
Yes.
Yes, perfect. Okay, so thank you for inviting me. It's a great honor to present at this community, and especially I'd like to be a bit more involved in this community. We, as I'll show, we're starting, the community is building up in the UK and Ireland and in Northwest Europe because the marine heat waves are building up. But first I thought I would just introduce what my team does. So we bring together atmosphere, ocean, wave, and biogeochemistry models at kilometer scale on several regions in the world. This is the UK. We also have a domain over India. And we've been developing this system for the last 10 years, and we're now starting to use it in climate projections, which is really exciting, and also using it to understand marine heat waves and feedbacks on land and on the atmosphere, which I'll present here. But first of all, maybe we are currently actually in a marine heat wave state, which has made the news this week. So on the bottom left here, you can see the extent of the anomaly. That's from the nice graphs that BBC produced with our data. So basically, quite a lot of this marine monitoring has started at the Met Office and National Oceanography Centre, and lots of research institutions in the UK has only started kind of in June 2023, when we had a very large marine heat wave, which looked quite like this one. With extreme marine heatwave conditions west of Ireland, and we also had the North Sea at that time. So, the research, we've basically had quite a lot of marine heat waves in the last 5 years, and that has spun up our research. And so we really want to learn from this community, further. And so, currently we have seen on the right, it's the average temperature from Ostia, the satellite project, for 2025, and you can see that the year is really at the top of the pack of all the curves. So we've seen unprecedented temperatures, which started in the winter, and then instead of the ocean usually for our area of the world starts only warming in mid-March, and this season started to warm mid-February. And we've had an exceptional spring, so exceptional weather conditions, which is very similar actually to what happened in June 2023, though this happened much earlier in the year. So what I'm going to talk about most, and another big point is that we have seen no marine cold spell since 2018. This is the Ostia average on the Northwest Shelf, and this is a very remarkable trend, as you can see here. So, what I'm going to present are two articles that have been on this June 2023 marine heat wave, which was really the biggest anomaly we've seen, and now we have another big anomaly now. So we've published this paper at the top in Communications, Earth and Environment, and then recently Thibaut Guinaldo in France has also published a paper on the whole of the North Atlantic, and I think the two studies are really complementary, so I wanted to present them together and show that we show similar things with different data sets slightly different approaches. So this was the June 2023 anomaly. On the left you can see the different categories, and we had some pockets of category 4 around the Irish coastline. In general, the whole domain was in category 1, and then the North Sea was category 2 with pockets of category 3, and all the western part of the domain here were in category 2 / category 3 or 4. And on the right here, this is the standardized SST anomaly in terms of standard deviation, how many standard deviation we are above, so how many standard deviation away from the main distribution we are on the right, which is Thibaut's paper. And what he was noting, which is very interesting, is that the anomaly was unusually centered in this horseshoe pattern, and this horseshoe pattern that he highlights in yellow is actually the part of the North Atlantic which responds faster to the atmosphere. All the western part of the North Atlantic is dominated by ocean circulation, and so is less driven by the atmosphere. So the whole of his paper is focusing on this yellow area and how things were extreme on this part of the North Atlantic. So going back to my paper, the Northwest Shelf, Northwest European Shelf, this is a time series with the different marine heatwave categories in grey, and in red you have 2023. It was the longest category 2 anomaly that we've had, for 16 days of category 2 and more than a month of category 1 as averaged over the Northwest Shelf. And we had the very strong trend at the start of the change from category 1 to category 2, with the second largest warming trend that we've seen in Ostia. And what is remarkable is on the right, if you look on the right, you see that if we take away the warming of the last 20 years, and that's the difference between this dotted line and the full line, then the marine heat wave would have only reached category 1 instead of category 2. And that's been a very strong message, is really, I mean, that's what the IPCC says is, the background warming is really pushing up the extremes to unprecedented levels. And so Thibaut then looked at this horseshoe pattern on the North Atlantic, and you can see that the anomaly was well above any anomaly that we've seen before. So he's put all the extreme years of the last 40 years as grey or blue lines, and 2023 really comes out as a very exceptional anomaly of 2-degree anomaly. And if you look at this on the right, in the climate context, he's taken all the large ensembles of CMIP6 and he's looked at the distribution pre-anthropogenic warming distribution and 1.3 degree warming, global warming level, which is the orange, which is roughly where we were in 2023. And he's put then the June 2023 anomaly, and basically without any climate change, it was not possible to happen. And even in this 1.3 degree world, it's a 1 in 100-year event. So it's still a very rare event that we've had on this horseshoe pattern. Then we've also looked at the stratification pattern, because obviously we know these are surface-based marine heat waves. And we were lucky to have gliders in the Northwest Shelf, operating in the Northwest Shelf. And in the bottom left here, you can see how shallow the mixed layer got. It was less than 10 meters for at least 15 days. So we had a very shallow anomaly. And on the right, this is from Thibault's paper. He's looked at the anomaly in the IAP dataset. He's looked at the stratification, and 2023 is an extreme stratification year. So it's not just the temperature, it's also the stratification, which is extreme. And we've both quantified that the stratification extreme has amplified the heat flux extreme by 1.75 in the Northwest Shelf and 2 times on that horseshoe anomaly. So we really needed that extreme stratification for an extreme temperature to happen. Then the second driver, obviously, is the stratification part, but there's also obviously the forcing part. And we've seen, using error 5 on the left, that on this domain, the sunshine has been strongest since 1975, and it's been the sunniest UK June, actually, since the records began in the 19th century. So a very, very sunny June. Obviously, it's also a time of peak for sunshine activity. And another factor was the weakest wave activity that we've recorded in our regional wave reanalysis. But the stratification, we were saying the stratification, this isn't now from our regional ocean analysis on the right, the ocean stratification before the event. So during the event was extreme, but before the event was more or less average if we take the last 10, 15 years. So we were saying there was not much stratification preconditioning of the event, but the event was an extreme stratification. So what led to this extreme sunshine and extremely weak waves? It's a series of anticyclonic weather regimes. So we have, for the northwest of Europe, a 30 regime, weather regime classification of 30 regimes. And you can see here, I've put examples. So that's the time series in June of the weather regime, and you can see the red ones are with anticyclonic patterns over dominating the system. And you can see it's been this weather regime 9 is actually the one we're experiencing currently with this extreme marine heat wave west of Ireland. It's very present. We've got this weather pattern 5 with a blocking over Scandinavia. And especially this weather pattern 16, we've shown that this is the one that is responsible for this very intense increase in the sea surface temperature. And it's got interesting reasons. So obviously it brought lots of sunshine, weak winds, but also there's a third factor that this weather regime brought, and it's tropical air that came over the Northwest Shelf and prevented the cooling from the ocean. Well, not prevented, but reduced the cooling from long wave cooling and latent heat cooling because of that tropical moist air. And even at night, we had sometimes cloud at night and bright skies in the day, which is probably the worst conditions for the ocean to just warm and not cool. And then actually, once the marine heat wave was formed, we had quite a few cyclonic, but weakly cyclonic events that didn't manage to break this very stable stratification. And it's only when we had stormy weather at the start of July that the marine heat wave really broke and then was mixed down. And it took about a month to get rid of the anomaly with a lot of storms. We've had a very stormy July and August. So with this study, we then triggered some PhD projects around this. One is looking at which weather regimes are driving marine heat waves in general over the Northwest Shelf, so that we can build also a longer range product for forecasting marine heat waves at about 10 to 14 days range. And the other one is how does ocean marine preconditioning impact storms that end the marine heat waves, because for our region, the end is usually quite dramatic with big storm. So it's how that marine heat wave feeds back on the storm. And I'll touch a bit on this, but this is Piali Goswami's PhD in University of Reading. Then look, Thibault found very similar conclusions, so I'm not going to go in details in there, but exceptional sunshine, low cloud cover, and low winds. And then another interesting question is whether, so we thought there was not much stratification preconditioning before the event, but then Thibault looked at a much longer time series in the IAP dataset, and he's shown that there is a trend for the North Atlantic in this horseshoe pattern region, a trend to stratify more, and this trend is driven by the temperature trend. So he quantified that this stratification trend, and you can see the extreme in 2023, but there is still a trend without even the extreme. So that trend contributed to about 20% increase in that intensity of the event. Finally, a very smaller driver, but still, you kind of add these little contributions and then get the extreme. Another contribution was a feedback on the stratocumulus cloud cover. So usually stratocumulus feedback is not necessarily observed in this region, but we've shown with counterfactual experiments of our weather system. So we've run the atmosphere-only system with the marine heat wave, without the marine heat wave, just a climatological sea surface temperature. And if you focus on the red here, the red represents the fraction of low cloud area, and you can see that it's higher in the climatological run than it is in the run with marine heat wave. So this means that the marine heat wave has reduced the cloud cover and enhanced the sunshine that it gets. So it's positive feedback, and we quantified it resulted in a 0.04 additional warming, which is small, but it contributed to maintain the marine heat wave state, whereas it would have declined without it. And then we also looked at the feedback on the weather over land, and we ran, as I said, these two experiments, one with, one without the marine heat wave. So it's a conceptual experiment, because obviously the sunshine was generating the marine heat wave, but we just wanted to know how the anomaly that is generated over the ocean propagates over land, and how much of it propagates over land. And this June broke monthly mean record temperatures by 1 degree in the UK, 0.9 degree, and which is very, very big step. Usually it's 0.1, 0.2 degrees. And we quantified the marine heat wave contributed to 0.6 degrees of that warming. And interestingly, despite the reduction in the land-sea contrast, when you have a marine heat wave, the sea breezes were stronger. And this is because the boundary layer height over the sea gets higher, and you can have a little bit more wind over the sea that is then transported with the sea breeze over land. So the sea breezes were a bit stronger because the land-sea contrast is still high enough to trigger them, and there's more momentum that comes from the ocean and is transported with them over land. So then we looked at also what does this anomaly look like in a climate change context, and we've put our regional climate change projections, and we've seen that quite strikingly in these projections, which are probably the most pessimistic that we can get for this area, in an RCP 8.5 scenario. This June anomaly would be averaged by the middle of the century, which is not far away. So it's quite a scary projection. And what Thibault did was also really interesting, is that he was looking at the anomaly on the left is what was observed, the anomaly that was observed for the month of June, and then he's placed this in the context of how the warming at 1.3 degree is expected to be from the models. And that's the warming pattern, sorry. So he's basically removed he's just taken away the mean of the domain so that you only see the warming pattern. So this figure shows that the Northeast Atlantic, this horseshoe pattern, warms less than the western part of the Atlantic. And this is because of the well-known warming hole. And basically, his message was that this anomaly is exceptional and is not the pattern that we would expect with climate change, but everything will warm, and so we will get to much warmer temperatures as we've seen in our projections, but slightly less than in the Western Pacific, Atlantic, sorry. So what are the consequences for weather over land? So I've talked a little bit about them for this June 2023, but we also looked at more marine heat waves, and the other one was May 2024. We've had a lot of choice because we've had, as I said, many marine heat waves recently. And we've seen a contrast because the marine heat wave in May 2024 was about half of the intensity of that of June 2023. But interestingly, the contribution was similar to the land warming. And we're working on this, trying to understand, which type of weather leads to more anomaly being affecting on land, and we think it's a difference in boundary layer height. We had a very cloudy May 2024, whereas it was sunny June 2023 over land, and the cloudiness seems to be able to propagate the anomaly from the ocean to land more easily because the anomaly from the ocean is not diluted by a high boundary layer over land. Another piece of work in progress is by Piali, and we've been looking at Storm Babette, which was a very intense extratropical cyclone that hit the UK and rained very heavily over Scotland and had lots of coastal hazards in Scotland. And you can see the orange, that's the marine heat wave of the autumn 2023. And the storm actually, as I said before, dampened this marine heat wave. And actually you've got another storm at the start of November, Storm Kieran, which further dampened and finally brought the SSTs back into the climatological range. So we've looked at we've run the couple system with the anomaly that you can see on the right here. We're trying to reproduce the austere anomaly, but with a couple system initial restart. So we've used 2020 as our climatological year. We didn't quite get the exact same pattern, but we get some of the marine heat wave anomaly. And then we've looked at the impact that this has on multi-hazards of the storm. So river flows, which we now have in the couple system, surge and wave height. And we've seen that all of these hazards were amplified by about 10, 20 or 3%. And so the idea is that this marine heat wave has amplified each of this multi-hazard a little bit, which led to these very damaging conditions at the coast for Scotland with quite a lot of erosion, and in some places 5-year worth of erosion. So we're writing this paper up. It's a very interesting study. And I will stop here, and I will just conclude by saying, our marine heat waves have really increased in the last 5 years in Northwest Shelf. And we are building our marine heatwave research community. We had our first meeting yesterday. We're building our monitoring and forecasting capability for marine heatwaves, basically visualizing things as anomalies rather than full fields. But it's quite a lot of work. And then because we haven't had a huge marine heat wave at the peak of temperatures, we haven't seen yet massive impacts on ecosystems, but we know the monitoring now is crucial, and we'd like to learn from the international community in terms of the impacts for your region and how we can translate that knowledge for our region and how we can try and anticipate and the potential potential damages by an unprecedented heat wave. Thank you.
Thank you. Excellent talk, Ségolène. I think our the first webinar we did the 2 talks, and then we opened for questions afterwards. If you agree, we can do that.
Yes.
Okay. So let's then invite it. Thanks a lot, and then hold your questions for Ségolène. We will. So our second speaker then, I'm introducing him, is Christoph Renkl. He's a climate scientist with a background in atmospheric science and physical oceanography. His research focuses on interactions between the atmosphere, ocean, and cryosphere within the climate system as an integrated role. Recently, Christopher joined the University of Bonn in Germany as an interim professor, where he's currently building the research group Regional Weather and Climate Modeling. He's particularly interested in combining couple numerical model and observations using a variety of statistical tools to improve our understanding of the climate system, including question of predictability, long-term trends, and extreme events. So during today's webinar, he's going to talk about intensification of atmospheric rivers by marine heat waves, multiscale air-sea interaction, and string effects on coastal and inland climate. So thank you very much, Chris, and please, the floor is yours.
Yeah, thank you so much, and thank you to the organizers for inviting me to share my research. This is part of my postdoc that I did at Woods Hole Oceanographic Institution together with Heatwaves. And this research is part of an NSF project funded to look at the coastal climate in California. So as I said, today I'm going to be talking about the intensification of atmospheric rivers by marine heat waves and look what these marine heat waves do on downstream effects when these atmospheric rivers hit the land. First of all, because I'm pretty sure most of the community that's gathered here today is not quite familiar, or is maybe not familiar with the term atmospheric rivers. I'll give a brief introduction about that. And as you are probably aware, the moisture on the Earth is not distributed equally. We have generally moisture surplus near the tropics. And here what you can see is a global map of total precipitable water. So this is your moisture content in the atmosphere integrated over the whole air column. And you can see that there are these filaments that are extending from the tropics into the mid-latitudes, and these are associated with low pressure systems that have these long and narrow filaments of increased moisture transport that we call atmospheric rivers. More formally, an atmospheric river is defined as a long, narrow, and transient corridor of strong horizontal water vapor transport that's typically associated with a low-level jet stream ahead of the cold front of an extratropical cyclone. So you can see here in this schematic, we have a typical low pressure system with a cold front and a warm front and an occluded front. And just ahead of this cold front, where you have warm and moist air brought from the tropics that is separated from the colder air that's coming from northern latitudes, where that sort of converge together. This is where we get these narrow filaments of strong water vapor transport. They they are termed these atmospheric rivers. So the key variable here is the integrated water vapor transport. So this is essentially your moisture transport, and again, integrated over the whole atmosphere. However, as you can see on this right-hand side sketch, most of the moisture is actually gathered in the lower 4 kilometers of the atmosphere. So these atmospheric rivers are generally a low atmospheric phenomenon. And oftentimes they are associated with a low-level jet. So these atmospheric rivers not only bring a lot of moisture, but they're also associated with a lot of wind. And so now, if you're, for example, in areas where this moist air is forced to rise, for example, when it hits a mountain range, as I will show is the case along the west coast of the US. You force this moist air to rise, and as it rises, it cools down, can't hold all the moisture, and therefore leads to a lot of rain. So atmospheric rivers are frequently associated with heavy precipitation in these areas. And the question is now, how do these atmospheric rivers interact with the ocean? And I will showcase this with a showcase of the Northeast Pacific with atmospheric rivers that made landfall during 2014 that coincided with a period where there was a strong marine heat wave in the ocean. As you can see here, I'm showing a series of atmospheric rivers that are again illustrated by the integrated water vapor transport and that are embedded in these low pressure systems that are propagating from west to east towards the west coast and then hit the coast there. And what you see in the background is these are your SST, so your sea surface temperature anomalies for that period. And we're looking again at December 2014, where the Northeast Pacific experienced a strong marine heat wave that I will talk about in a second. As everyone probably in this round knows, marine heat waves are typically defined as discrete, prolonged, anomalously warm waters at a particular location. And they can be defined either with a fixed threshold or seasonal varying thresholds, percentiles, or and then classified into categories. And one disclaimer that I'll do here is I'm using the term marine heat wave very loosely. I'm essentially just looking how do positive SST anomalies interact, or what's the role of positive SST anomalies on these atmospheric rivers. So, but we know that in December 2014, which is the period I'm looking at, the SSTs were exceptionally warm and there was a strong marine heat wave in the Northeast Pacific. And this marine heat wave, I'm sure you're familiar with you're very familiar with this. It started out as the infamous blob in the central Northeast Pacific that was mainly caused by deflected storm track, reduced mixing and entrainment, and also limited seasonal cooling, similar to what we heard in the previous talk. And then as the atmospheric circulation changed, this warm SST anomaly propagated towards the coast and essentially built this, again, a horseshoe pattern, this time in the Northeast Pacific. This is similar to a PDO pattern with warm anomalies stretching all the way from Alaska down to Mexico with exceptionally high SST anomalies that obviously had unprecedented impacts on the marine ecosystem and fisheries. And on land, this coincided with long-lasting drought conditions, particularly in Southern California. So overall, these marine heat waves make the propagation or the landfall of the ARs in Southern California or along the US West Coast unfavorable. That's because, as I've talked about, the storm track is deflected. However, in 2014, there was a series of ARs, as I showed in that animation before, that did propagate over the exceptionally warm ocean. And so the question is, what is the impact of this marine heat wave on the ARs that made landfall, and what are the downstream effects on precipitation? And why this matters is, as I said, most of or especially Southern California was under exceptional drought conditions. So in a sense, these atmospheric rivers brought rain or precipitation to the area that was much needed. However, it came in amounts that was not favorable for the environment, and therefore led to flooding and erosion events there. And that just goes to show that these atmospheric rivers can be fortunate events for these dry regions, but can also be very dangerous. One thing that has been shown before is that the SST do impact the coastal precipitation along the west coast. So Elise Baudin et al., they used a modeling study where they prescribed a PDO warming pattern to an atmospheric model and showed that in the mean conditions, when you prescribe these warm SSTs, you get an increase in the mean precipitation. And they attributed this change mostly due to the change in an adjusted large-scale atmospheric circulation, rather than more moisture, which would have been a thermodynamic effect. And similarly, there's also observational studies that looked at the air-sea interaction or around the time when these ARs made landfall. For example, here, Sam Bartosek and others, they showed that before the ARs make landfall, which is at the time equals 0, so in the 2 to 3 days preceding preceding landfall, there's enhanced latent heat flux that's modified by SST anomalies in the ocean. And this just goes to show that there is some air-sea interaction happening as these ARs propagate over the ocean. And we want to understand now how does what's happening if the ocean is under extreme conditions during a marine heat wave. And we do this using a coupled atmosphere ocean modeling approach using the SCORE model, or also Scripps coupled ocean atmosphere regional model that combines a weather model based on WRF, so weather research and forecasting model, and a regional ocean modeling system, ROMS. I'm not going to bother you with the details of the model here, but I just want you to know that I'll be focusing all the analysis on the coupled domain that's embedded in a larger atmospheric only domain. And this domain has a 7.5 kilometer grid spacing where the ocean and atmosphere talk to each other every hour, exchanging heat fluxes and momentum fluxes and moisture fluxes based on the core 3.5 Bloch flux algorithm. What we want to do with this coupled model is we want to model two different cases, one with and one without marine heat wave. So in order to be able to extract the marine heat wave from our coupled system, we first of all have to define it. And we do this by subtracting the initial SST we subtract the climatology from our initial SST field, which gives us our SST anomalies. And as you can see, that there is, again, this large-scale warming pattern, but there's also a lot of small mesoscale structure in the SST field. The problem is now, if we remove the entire field, including all the mesoscale structure, then the coupled model would take some energy to regenerate these small structures, and we wouldn't be able to cleanly attribute our results to the marine heat wave, because there would be some spin up needed for the mesoscale activity to regenerate in the model. Therefore, what we decided to do is we applied a large scale filter to the SST anomalies here using a 5 by 5 degree lowest smoother, and only subtracted this large-scale marine heat wave from the model anomalies, which gave us still small-scale marine or small-scale SST anomalies, but without a large-scale marine heat wave pattern. So now we have two sets of initial conditions that have one has a large-scale marine heat wave and the one has no marine heat wave in it, that we then add on to the climatology again at the initial conditions. And we run our model for 20 days and generate 11 ensemble members per case that we generate by shifting the initial the initial conditions by 1 to 5 hours around that initial date, just to get a sense of the internal variability of the system. And this is what the model says happened. What I'm showing here in the top are daily snapshots of multiple ARs that made landfall during the period of December 7th and December 12th. So it may look like one AR that sort of slowly approached the coast, but these are actually multiple pulses of increased IVT that made landfall over this period. And you can see that better in this Hofmüller diagram in this middle or in this lower panel, where I'm showing time as the x-axis and latitude as the y-axis. And this is now averaged around the coastline, so plus minus 50 degrees around the coast. And you can see that there is, whenever there is color, we exceed the AR threshold of 250 IVT units. So we can see that large parts of the coastline from Northern California all the way to the Canadian border were under AR conditioned with extreme intensity, where the maximum IVT exceeded 1,000 kilograms per meters per second. So in this, similar to the marine heat waves being categorized, the ARs also have categories that depend on the intensity and the duration of the event. And our model suggests that this was a category 3 event. So now when we take the difference, when we look at the difference between the case with and without marine heat waves, we see that there is a large scale increase in the presence of the marine heat waves. So in the bottom, you see the differences where positive values mean that in the presence of the marine heat wave, you had more or stronger IVT, so integrated water vapor transport towards the coast. And this IVT increased mostly at the beginning and the end of this series of ARs, and at some places increased the intensity of ARs by up to 54% in the presence of the marine waves. And while overall the duration of the event was comparable, just varied by a few hours, the maximum intensity was definitely reduced without the marine heat wave, and effectively downgrading, or without the marine heat wave, it would have only been a category 2 event. So this is sort of a hint that the marine heat wave leads to an intensification of these ARs. And another way to look at it is at the downstream response. What I'm looking here at is the mean hourly precipitation rate for 5 different latitude bands, now averaged over the 100 kilometers or the first 100 kilometers inland. So each of these bars is the hourly mean precipitation rate of the ensemble system, where blue colors refer to the marine heat wave case and yellow colors are the no marine heat wave case. So wherever you see blue poking behind the yellow bars means that there was stronger precipitation in that particular time in the marine heat wave case. And then we can also integrate over this period and see that, and this is shown by the solid lines where the spread is of the differences between the marine heat wave and no marine heat wave cases indicated by the shading. And there's a few things we can take away from this plot. First of all, the precipitation clearly starts earlier in the presence of the marine heat waves. Most of the time, particularly in the southern part of the coast, the peak precipitation rates are stronger, and this obviously then transfers or translates into an increase in accumulated precipitation, where interestingly the precipitation doesn't change like uniformly along the coast, but especially the very dry regions around Southern California experience, in the model at least, an increase in precipitation of more than 50%. So where does that come from? Now, what we're looking at is at the mean model conditions over the period from basically of the last 2 of the 3 weeks of the model simulations. In the top plot, you can see the upward latent heat flux. So this is generally positive, so it means the ocean is generally losing heat to the atmosphere. In the bottom, I'm showing the differences between the marine heat wave run and the no marine heat wave case, where red colors indicate more latent heat flux into the ocean, into the atmosphere. And the marine heat wave pattern is sort of indicated by this black line. That's the 0 line of the SST anomalies that I showed before. So everything to the east of the black line is where we had positive SST anomalies. And in this area, we clearly see an increase in latent heat flux. And the evaporation that's associated with that provides more moisture or increases the moisture content in the atmosphere, that once these storm systems propagate through this increased moisture, will pick up the moisture, transport it over land, and when it hits the coast, there leads to more precipitation, as it's shown here. We can look at that in a more quantitative way by looking at the mean moisture budget of the atmosphere. And what this says is that the difference between precipitation P and evaporation is proportional to first order to the moisture flux convergence integrated again over the entire atmosphere. So whenever this you have moisture flux convergence, so that this entire integral becomes positive, your precipitation is larger than evaporation. We can split this up into a mean contribution due to the mean moisture, but also due to the mean mean advection of the moisture, but also the mean advection of the mean winds, and an eddy part, and a small part that we are typically neglecting. If we now apply this moisture flux or these moisture budget to our model anomaly, our model results, we can see that generally in the northern part of the domain, we see convergence, so more precipitation than evaporation, whereas in the southern part, we see divergence, which is, sort of spreading away from of the precipitation. If we now look at the difference in the moisture flux convergence between the marine heat wave and the no marine heat wave run that's shown here, then the brownish colors mean that over the ocean, there is anomalous divergence. So there's more moisture being removed from over the ocean, and green bluish colors mean anomalous convergence over land. And you can actually look at that even further and decompose it even further and look at the differences between the contributions of moisture and the winds. And what we found is that it's primarily the increase in moisture that's provided by the increased evaporation from the marine heat wave that's then picked up and brought towards land. And then there leads to anomalous convergence and therefore anomalous precipitation. So overall, we have used a coupled ocean atmosphere modeling approach to simulate AR events during the marine heat wave in 2014 winter. And we've shown that the marine heat waves increase the mean latent heat flux that provides more moisture that ultimately leads to more precipitation. So this additional moisture provided due to the increased latent heat flux by the marine heat waves actually amplifies the ARs by more than 50%, as we've seen. And this translates to an increase in precipitation inland. So, and as a last thing, what I showed was that there was more moisture advected away from the ocean that's then accumulated over orography. As the next couple of steps, we would like to further address the large-scale structure of the SST anomalies. If you remember, there was this slight cold pool of SSTs and the warm pool. We want to examine what is the relative role of the warm versus the cold and the gradient in between. And obviously, as these storms pass, and this I think also ties in nicely with the previous talk, is how do these ARs or these storms in general contribute to the marine heat wave dissipation? But this is all work for the future, and I'm happy to take any question. And thank you again for the invitation to present this work here.
Thank you, Christoph. And yes, excellent talk, both. And so I will open the floor for questions. Okay, we have hands. Oh no, it's just clapping. Have lots of them. Any questions? Oh yes, Carlos.
Hi, my name is Carlos Moffat. Thank you for two excellent talks. I'm mostly working on Antarctica, so I'm interested in this topic, but I don't know very much about the regional systems that you're looking at. To the first speaker, I was wondering, again, I don't know much about the oceanography of that region. Of course, you talked a lot about advection being important in the atmosphere, and I was just wondering if you think that the advection in the ocean has a big role in setting that anomalies in mixed layers that seem to be quite important for the development of the heat waves. That's it.
Yeah, thanks. So basically, the marine heat wave developed too fast for it to be influenced by ocean circulation. So it was mostly atmospherically driven. So, I mean, that said, for example, the marine heat wave we're seeing now has also obviously been preconditioned by warmer sea. And that's a combination. So the background temperature is a combination of ocean dynamics and atmospheric forcing. I think around the UK and Ireland and the Northwest Shelf, what is interesting is that some of the regions have very strong tidal currents, and so they can't stratify. And so we're finding that the marine heat waves, obviously in these regions, have very different characteristics to the water that can stratify. So that introduces quite a large gradient, spatial gradient in the marine heat wave states of the water, with the English Channel being fully mixed and can't stratify and takes a long time to build up marine heat waves and to cool them down. So it's quite interesting having very different hydrodynamic regions, actually.
Thank you.
Thank you. So next question, Alex.
Thanks very much. They were fantastic talks. I had a question for Christoph. You mentioned an earlier study that sort of put a PDO pattern in there and found that the effect was largely dynamic, whereas your one seems to be mainly thermodynamic. I was just wondering why the difference.
Yeah, I think that's mainly because of the different timescales we're looking at. So I'm looking at individual events that sort of pick up the mean moisture or the increased mean moisture content that's sort of in the background, whereas Elise in her paper, there the entire atmosphere had already adjusted to that additional warming from the atmosphere that we essentially don't allow for with these short model runs. So I think they don't necessarily disagree with each other, but they're sort of they just look at two different time scales, and that's I guess an interesting point of this is that the response of the ocean of the atmosphere to these marine heat waves might differ depending on which time scale we're interested in.
Thanks.
Antoniette, I think it's you.
Yes.
Okay.
Yes, in incognito with my Colorado University email. Yeah, thank you so much, both Ségolène and Christoph, for these great talks. So I have a question for Ségolène. I think that, so you actually touched on several interesting aspects of the connection between like internal variability and climate change. So on one hand, we have this warming trend, which raises the level of temperature and makes, the maximum temperature more extreme. But then also the consequences of that are this increase in stratification, at least in areas where there are no tides or there is not much mixing, which then can enhance the surface temperatures. But then you also talked about these anticyclone weather regimes, and I was wondering if those also maybe, if there is any more increased frequencies of those weather regimes that can then cause this warming. And if there is any indication that those conditions can become more common.
Yeah, it's a very good question, because indeed the the warming trend in the recent years has increased, and I think that's probably more decadal variability rather than climate change. Though there's a nice study by Robert Votard who has shown that we've got an increase in anticyclonic weather regimes for Western Europe. We've had an increase, for the last, I can't remember exactly, but there's been an increase of more sunshine for Northwest Europe because of more anticyclonic weather regimes. And we don't know yet, with our models, none of the models show this increase expected with climate change. So we don't know whether that's just climate variability, that just decadal variability and will come down, or whether it's a climate change signal that is not captured by the models for Europe. So it's an open question, but there is a mix of the two. In especially this region has quite large decadal variability. So there's probably, we are in like this last 5-year period is sunnier than usual. Yeah.
No, because there is a comparison with the Northeast Pacific that Christoph was talking about. I mean, he mentioned this extreme dry condition of California, and so there was this persistent ridge whose presence was associated with this forcing of these marine heat waves, but was also associated with the lack of storminess precipitation over California. And I think people have speculated that these conditions may become more frequent. So it's another aspect that maybe weather pattern, whether they can become more common, and this would be another way by which climate change can affect other extremes.
Yeah, because in our region, they're not projected to change a lot, but they are changing at the moment quite a lot. So there is that, yeah.
Thank you.
Okay, thank you. I think we have someone else. Is Zheng Zheng from Howard University?
Yeah, hello. I have a comment about the PDO connection with the warming in the North Pacific Ocean. Actually, whenever you do the UF analysis, you will see that the pattern of the warming in last decade, almost no projection to the PDO pattern. So the warming pattern in the North Pacific Ocean is totally a different pattern from PDO or even the second mode we always mentioned in our lecture. So it's a different pattern of warming in the North Pacific Ocean. That's the comment. And for the first talk, I have a question about look like the weather pattern play a role. I think this probably associated with the North Atlantic oscillation, some like pattern. I just want have you checked the predictability of the marine heat wave in this area? Thank you.
Christoph, do you want to go first? Or...
Yeah, I think, I just wanted to clarify maybe that with the modeling studies, or at least in my modeling study, I'm not saying that the warming that there was due to the PDO. This was just the pattern of the marine heat wave that existed at that time. It just had this sort of like horseshoe PDO like pattern that with the warming pattern, it's clear that this doesn't necessarily have to project on this mode of variability. So just to avoid any confusion.
For your question, so Thibault found that the SST anomaly projected quite well on the main mode of variability for May and June, but the atmospheric forcing did not project on the summer NAO at all. It was a series of weather regimes that are just unprecedented, hasn't been seen really before. So, I mean, the particular series hasn't been seen, not the weather regime itself. So we had very little predictability for this marine heat wave. We are investigating whether we can have gain 1 month predictability, but we in this region it's very hard to get more than that. So we're working on trying to have 1 month of seasonal predictability. I mean, obviously, it was also in the context of the very large 2023 and global warming, very stark. And there the models had a bit of a few models did manage to predict this very large increase in May, June, but only like a handful of them out of hundreds of seasonal predictions. So difficult predictability and not more than 1 month. Yeah.
Yeah, actually, that is the similar case for the blob in the North Pacific Ocean. I think we published a paper in Journal Climate some years ago. We found that even 1 month lead forecast, most of the forecast member made a wrong prediction. So that is the challenge for the prediction of the equator area for the marine heat wave. Thank you.
Yeah, it's just the jet stream decided to behave differently suddenly, with no warning, basically. Yeah.
We are 1 minute past, but there is one last question, if you don't mind to just stay and then respond to one more question. I guess it would hurt. Gaiti? Yeah, Gaiti. Sorry if I pronounce wrong your name, please. Hello? Maybe it's maybe it's a wrong line. But I just want to add then a quick then comment on this last comment or question for Ségolène. I know that there are some studies that show that we have more increase on high wave number. Rossby wave kind of in the northern hemisphere, particularly in this sector of the Atlantic and European, which leads to this kind of more heat waves over Europe. And I wonder if that is one of this, because then you have a high pressure center followed by low pressure and so forth, so on, and sometimes they get stuck when they create the conditions for the marine heat waves, and I'm not too sure if the climate models can simulate this. Do you have any idea or comments on this aspect that could be related to this kind of a dynamic?
Yeah, I mean, certainly the climate models struggle to generate blocking over Western Europe. They have low frequency bias. I mean, yeah, they bias low in terms of their frequency. For the whole Rossby, so you were talking about the whole hemispheric Rossby wave number. Yeah, I'd be interested to see the paper. I wasn't aware, but yeah, the two are connected. And I mean, for the global anomaly, I know there's a nice paper by Jens, I can't remember his name, from University of in Switzerland, and they've shown that 10 out of 10 CMIP models managed to reproduce that very large jump in 2023 in the fall, and that most of them had also North Atlantic anomaly in them. So some of the models can do this big jump, but 10 was out of 10,000. So they said the probability was very, very low of that event. So we can, but very infrequently probably. And we still need to work on our models for that, yeah.
Okay, I guess that's it then. I would like to thank again our two speakers, Christoph and Ségolène, for your time and then be here with us. It was great and very, so thank you. We can.
Thank you very much.